Welcome to Explained on Paper, where we explain things on paper. So, today's topic is the Miller cycle and dynamic compression ratios. Now, what's the Miller cycle and what are dynamic compression ratios, or DCR? Well, a dynamic compression ratio, it's similar to a regular compression ratio, but we'll get to that in a moment. The regular compression ratio is basically, as you can see on the screen, I'm drawing a bit of an engine. Now you can see the piston at the bottom. The piston is at bottom dead center, and you can see the intake valve on the left and the exhaust valve on the right. The piston is now about to begin its compression stroke. That means the intake valve is closed, and the exhaust valve is closed, and the air in blue, which we're about to see being drawn, the air in blue is going to get compressed into the combustion chamber. So the compression ratio is the relation between the volume of air that enters the cylinder and the combustion chamber volume. So you divide the combustion chamber volume, which is pictured in red, by the pictured in blue drawn air or displacement volume, and that gives you the compression ratio. Now, the compression ratio means basically horsepower and torque. So higher compression engines tend to be of higher performance. That's like an oversimplification of what actually happens, but let's stick with it. So what is the dynamic compression ratio? Well, it's basically the real or actual compression ratio your engine has. Like, for example, I'm drawing a piston here. I'm drawing a cylinder and a piston and a cylinder. Okay? So while that's being drawn, I want you to look at it. There's the piston. It moves up and down. And there are the intake and exhaust valves with their runners. Spark plug in the middle. Now, there's your combustion chamber. And that's the air drawn in. But wait! What happened there? The piston moved up a bit. And that's the point. Ideally, the intake valve would close when the piston is at its lowest point, which is called bottom dead center, or BDC. But sometimes the intake valve closes after the piston has begun rising again. And that has many purposes. The main one is to do something called the Miller cycle, and the Miller cycle, I'll get to this in a moment, the Miller cycle is basically to improve fuel efficiency, and I'll explain a bit of that later. So right now we're getting our diagram of the four strokes, intake, compression, combustion, and exhaust. We all know that. But watch the intake drawing. Notice that and watch the compression drawing. The valve is still open, and yet the piston goes up a bit. And then the valve will close, the piston will actually start compressing air, and it'll explode and move the piston downwards, and then the cycle will continue. So that's what the Miller cycle is. It's actually running an engine as if it were smaller, because that's actually what you're doing. You're running an engine as if it were smaller. Now that's all well and good, but what's that stuff for? Well, it's actually for a lot of things, mainly fuel efficiency. The Miller cycle is used by Mazda and other manufacturers in their economy engines, and it's quite a common thing. In fact, the dynamic compression ratio of most engines is lower than their normal regular compression ratio. So, why have higher compression in an engine? Well, it, in a nutshell, makes more power and more torque because you're burning more fuel. Why would you want less compression? Because you're burning less fuel, and that's what the Miller cycle is. It draws in the same or less air, and it uses less fuel, so you can run less fuel, be more fuel efficient, and still have a larger engine. Now, a lot of engines that do this have something called variable valve timing, which allows the computer to, change the timing a bit and improve efficiency at lower RPMs. So, Miller cycle. it's reducing the size of the engine, basically. And that's exactly what it does. It compresses less air so you can run less fuel, making your engine behave like a smaller engine. And you do lose horsepower, but not that much torque, and that's the point of it. And furthermore, this Miller cycle is used in like a ton of economy cars. One example is the Mazda Skyactiv engines. And as you can see in the drawing, we have two cylinders, and you'll get what I am saying about drawing less air. The first cylinder, the one on the left, is basically the air drawn in by the piston. But this cylinder on the right that you can see right under my hand is the air drawn by the cylinder, but then without the part of the piston forced out while going up. Okay, but how do I calculate it? Well, it's quite simple actually. Now we'll ignore some of the things I've written here, mainly because my handwriting is so messy, but basically, let's remember that your displacement is calculated pi times bore halved square. It's just like the area of a circle. Bore, half it, square it, yeah, and multiply it by pi. That's the area of a circle. So, knowing that, we have your regular compression ratio is calculated like this. You get your combustion chamber volume, which can be figured out by a variety of methods, and then you get your drawn volume or your displacement, and that displacement is equal to bore halved times bore halved square times pi, and that you multiply by the stroke and you get your volume, you get your displacement. Alright, now let's do the math for the shortened, quote unquote, or adjusted stroke, meaning the actual volume of air that's getting compressed and not forced out of the cylinder because the valve's still open. That volume of air is basically the same circle area that we calculated for the bore, but we now have a shorter stroke. Now here's a recap. The shorter stroke is calculated by using the degrees of the crankshaft in terms of valve timing. For example, if the valve closes at 25 degrees after the piston hits bottom dead center, we're gonna go stroke minus sine of 25 multiplied by half of the stroke. And that gives us the shortened stroke, or the adjusted stroke. And then we multiply that by our circular area of the bore, and then we get the adjusted volume, and that volume divides the combustion chamber volume. So, quick recap. Adjusted stroke. Sine of the stroke minus sine of the angle times half the stroke. And that gets multiplied by the area of the circle, and that gives you your actual or effective draw. Hope you liked the video.